So I am a principal investigator in the Simons collaboration in arithmetic geometry, number theory, and computation. And I'm hoping that most of you in the audience are at least familiar in some sense with what number theorists do and what computation is about. But I suspect not everyone is familiar with arithmetic geometry, so I thought I would start by saying a few words about arithmetic geometry. So arithmetic geometers are interested in solutions to polynomial equations, typically polynomials with integer coefficients. I've shown you some examples on the screen. Some of them look very simple. Some of them may be a little more complicated. This is a rich subject that number theorists have been interested in going back to Diophantus and the ancient Greeks. But maybe to motivate, although this is a somewhat recursive motivation, but maybe to motivate why such equations are interesting and why this equation here is particularly interesting, is that these equations can actually encode or information about the existence or non-existence of certain other mathematical objects. Mathematical objects like curves that are defined by equations like this. So this example here is known as the cursed curve. It's a modular curve of level 13, although the 13 is not really why it's cursed. It's called the cursed curve because it, for many years, defeated all known attempts to determine all of the rational points on this curve. But this problem was solved last year by Jennifer Balakrishnan and her colleagues, who Jen is also a member of our collaboration, who were able to determine that all of the rational points on this curve, and by doing so ruled out the existence of a certain set of mathematical objects that everyone believed did not exist, but couldn't prove it until we knew that there were no rational points on this curve other than ones that have already been accounted for. Now, when I talk about solutions to polynomial equations, the first question that might come to mind is what kind of solutions are we interested in? And if we're interested in solutions over the complex numbers, well, there's already a well-established theory for understanding problems like these. In particular, the equations I showed you on the previous screen all correspond to one-dimensional algebraic varieties, so they're curves. And if we view them as varieties over the complex numbers, they correspond to Riemann surfaces. They're one-dimensional complex manifolds, but as real manifolds, they're two-dimensional, the surfaces, and these are classified according to a topological invariant, the genus, which you can compute just by counting the number of holes in your surface. So a genus 0 curve corresponds to a sphere. It has no holes. And then we have a genus 1 curve, genus 2, and genus 3. And I suspect we have a few algebraic geometers in the audience, and for an algebraic geometer, the first thing they do when they see a screen like this is they probably, in their head, are saying 0, 0, 1, 2, 3, 3. And that's the genus of these curves. And someone who spends a lot of time thinking about problems like this can, at least for curves that are in nice forms like these, can read the genus off almost immediately upon seeing the equation. Now, number theorists are really interested in not just complex solutions, but integer, or at least rational solutions. And this makes the problem much more difficult. In fact, it makes it unsolvable in general. This is a consequence of the negative answer to Hilbert's 10th problem. In the 1900 International Congress of Mathematicians, Hilbert famously proposed 21 questions which were meant to stimulate mathematical research in a number of different areas. His 10th problem asked whether there was a general algorithm, an effective method for determining all of the integer solutions to a system of polynomial equations with integer coefficients. In fact, all he wanted to know is there an algorithm to determine whether there are no solutions or there's at least one solution. And it took 70 years, but we now know the answer to his question is no, there is no effective algorithm. This problem is unsolvable. However, it can still be solved in many cases, including a lot of the cases I want to talk about today. But one thing you can always do, no matter how complicated the problem is, if you're given a system of polynomial equations with integer coefficients, you can always reduce those coefficients modulo your favorite prime p, and then you can count solutions modulo p. There's only a finite number of possible points you need to check, and you could naively iterate through all of them and count how many different points satisfy your system of equations. And this may sound like a trivial thing to do, but in some ways it's a big step forward, because there's a sort of a dirty little secret among mathematicians, which I will share with you. Most mathematicians won't admit to this, but there's really only two things we know how to do well. We know how to count, and we know how to do linear algebra. It's only a slight exaggeration to say that the rest of mathematics is devoted to reducing hard problems to one of the two things we know how to do well. And I've just reduced this problem to something we know how to do well, which is to count. Now, you might ask, well, which prime p should we pick? And the answer is we should pick all of them, or at least all but finally many of them. And we can then assemble these point counts into what is known as an L function that encodes a lot of fundamental information about the problem we're interested in. And it's fundamental in the sense that it's invariant under any sort of transformation we might make to the problem. Even if we rewrote the same problem using an entirely different set of choice of coordinates, maybe even a different number of variables, different number of equations, we would still get the same L function out at the end. And this L function can tell us a lot, not only about the problem we're interested in, but how it might be connected to other objects in the mathematical universe. But before we dig into L functions, let's start at the beginning and just count some points. So we'll start with maybe the simplest, not completely trivial example. Let's count points on this quadratic equation x squared plus y squared equals 1. So you should think this is the unit circle. That's easy to understand. We're going to reduce our coefficients mod p. That's easy because they're all equal to 1. And then for each prime p, we could count how many solutions there are. So for example, for the prime 2, x and y can't both be 0, and they can't both be 1, but as long as one of them is 0 and the other is 1, we get a solution. So we get 2 points mod 2. Mod 3, we get 4 points, and so on. You can verify these counts yourself if you wish. And what one finds after doing this for a while is that you always get, the answer is always p plus or minus 1. Now, it turns out that there's a better way to organize our point counting. Rather than counting points on this curve, we should instead homogenize the equation and count points on the projective curve, x squared plus y squared equals z squared, where we're only going to distinguish points up to scalar equivalence, and we don't consider the all 0 vector as a projective point. That's not allowed. And when we count points in this way, we find that, in fact, we always get the same answer mod p relative to p. We always get exactly p plus 1 points on our curve. And I said that you can then assemble these point counts into an L function that is going to tell us something interesting about the problem we're studying. And in this case, the L function we get is formed by taking a product, what's called an Euler product, of this form 1 minus p to the minus s, all raised to the minus 1. S here is to be a complex variable. This Euler product is equivalent to this Dirichlet series, which is the definition of the Riemann zeta function. So by taking this trivial example and counting points on it, we're suddenly led to a very deep question in number theory, one that we still don't know the answer to, which is where do the zeros of this function lie? There's a $1 million prize waiting for anyone who can answer that question by saying that they all lie on the line that we expect them to lie on. Now, you might say that, well, wait a second, that doesn't really have anything to do with this curve, and in some sense it doesn't. What this is really getting, the question that's being gotten at here is the primes, the sequence of primes that we're counting on. But for the curves I want to consider, the point counts will contain information both about the primes and about the curve that we're interested in, or more generally about the algebraic variety that we're interested in. The point of this example is merely to persuade you that there is something interesting going on in these L functions. Another fact which should persuade us that genus 0 isn't very interesting is that we always get the same L function. No matter which genus 0 curve we write down, we're always going to find that when we put it in projective form and count points, we always get p plus 1 everywhere, and we always get the same L function. So we should leave behind genus 0 and move on to the next simplest case, genus 1. So genus 1 curves are, provided they have at least one rational point, are known as elliptic curves. And if this were a number theory seminar, this would have been my first slide, because every number theory talk worthy of the name should begin with the sentence, let E be an elliptic curve. And you might say, how can that possibly be? Well, the reason is that elliptic curves are in many different senses the first interesting example. They're the first interesting example of curves. They're the first interesting example of abelian varieties. They're the first interesting example of many things that mathematicians are interested in. And also, there's a very practical reason why you should be interested in elliptic curves, because everybody in this room, I think I can say almost with great certainty, uses elliptic curves every day. In fact, I suspect most of you use elliptic curves every hour. Some of you might even use them every few minutes. Every time you do almost anything with your phone or your computer, you are using an elliptic curve. So just to demonstrate this to you, let's see what elliptic curves have to do with, I don't know, let's take the Simons Foundation website. So if I go to this little green lock icon here and click on it, it'll give me information about how this internet connection is being secured. And if I click the arrow here, it'll tell me about the certificate, the digital certificate that is securing this connection. And then if I'm brave, I will click on the More Information button. And I will say information about this digital certificate, when it expires, and then a long string of gobbledygook. But let me parse this for you. So these first three letters, TLS, that stands for Transport Layer Security. The next block of letters begins with the two we're most interested in. EC stands for elliptic curve. That means elliptic curve ephemeral Diffie-Hellman. The next three letters, RSA, are the names of the three inventors, Ravesh, Shamir, and Adelman, of the RSA protocol for digital signature verification, public key cryptography. With AES, that's the advanced encryption standard, using the 128-bit form. GCM is the Galois counter mode. This is a mode for the symmetric cipher that's being used to secure the connection. SHA-256 means the secure hash algorithm, the 256-bit version, although Simons is only using 128-bit keys to secure this connection. But if you went to a different site, you might find a larger key size, like 256 bits. But perhaps the most important part of this protocol is this ECDHE. Virtually any website you go to, I invite you to check out your bank or your Gmail or Twitter or whatever, Amazon, whatever you use to conduct your business on the internet, and see the string of letters that you get here, and the odds are very good you will see that it starts with TLS ECDHE. Okay? This protocol provides what's known as perfect forward security. It ensures that a new secret symmetric key is used for every session that you're establishing with the vendor that you're speaking with or sending your credit card number over, even though there is a single public key pair that is authenticated with RSA that allows you to authenticate who the vendor is. Okay? All right, but that is drifting into another talk, so I will come back to the question at hand. But hopefully I've convinced you that elliptic curves are worth caring about, even if you're not a mathematician, you use them all the time. Coming back to the problem of counting points modulo p, if we do this on a genus zero curve, we found that we always got p plus 1. And p plus 1 we should sort of think as the default value. That's what we should expect to see. And with an elliptic curve, now something more interesting happens. We don't always get p plus 1. We get something that differs from p plus 1 by a quantity ap, which is known as the trace Frobenius. And that you should think of this as sort of an error term in the point count. It's measuring how far we are from the expected number p plus 1. And as conjectured by Emil Artin and proven by Helmut-Haas, the trace of Frobenius is an integer that is never bigger than an absolute value than 2 times the square root of p. So given that we know that our trace of Frobenius lies in an interval between minus 2 root p and 2 root p, it's natural to rescale our Frobenius trace by dividing by the square root of p. This will give us a real number that's sort of consistent even as p varies. It's going to be a real number between minus 2 and 2. And so now you might ask the question, how does this real number vary as we let p range over all primes? What happens? Well, I've done this experiment for you. I've looked at the primes up to 256. In this table, you can see for each prime p, I've counted points on that elliptic curve. I take p plus 1 minus the number of points, gives me the trace of Frobenius, and then I've rescaled it to get this value x sub p, which you should think of as a random variable that's indexed by primes. And I'm interested in the distribution of this random variable. Now, looking at this table, it's hard to see any sort of distinct pattern other than maybe it seems to be positive half the time and negative half the time, roughly. The problem, of course, is we don't have enough data to draw any conclusions, so let's go get some more data. So to make it easier to view this larger collection of data, I've plotted it in a histogram. So the x-axis here ranges from minus 2 to 2, and I've chopped that histogram, that interval up into buckets. Here I'm using 13 buckets, which is roughly the square root of the number of data points I have, which is sort of a statistically good number to choose. I have 170 data points because I'm looking at all the primes between up to 2 to the 10, up to 1024. And then I've plotted the height of each bar in the histogram represents the number of normalized Frobenius traces that fell into that bucket. And then down at the bottom, I've computed a sequence of moments. These are the expected value. The first moment, 0.051, is the average value of the normalized trace, then the average value of its square, its cube, and so on. Now, looking at this picture, the gray line there is sort of the average. If it was uniformly distributed, we would expect to fill in that gray rectangle. And looking at this picture, it's still there's not really enough data to draw any conclusions. So let's go get some more data. So in each frame, we are doubling our bound on the prime. You can see that in the top up here. This number is going up. So we're getting more, counting points on more and more reductions of this elliptic curve. And you can see that as the bound on our prime goes towards infinity, the distribution appears to be converging to not to filling in the gray rectangle, but to a semicircle. And the moments are converging to what appear to be integers, a sequence of integers 1, 1, 2, 5, 14, 42. And for some in the audience, that'll immediately trigger the words Catalan numbers in their head. But these are a famous sequence of integers that pop up in all sorts of different scenarios. Now, you might suspect, well, before we look at some more examples, I should first note that this is a lot of data. We're looking at about 412 billion data points. We took all the primes up to 2 to the 40th. It didn't compute those on the fly. Nevertheless, it didn't take that long. This computation using the state-of-the-art algorithms we have at our disposal now is probably less than a week of CPU time to do this for one curve, and probably you could even do this in 2 or 3 days now. I haven't run it recently. But you might think, well, maybe I cooked the books. Maybe I cherry-picked this particular elliptic curve, knowing that it would give you a nice semicircle. So let's take a different elliptic curve. How about this one? So this is defined by the equation. Looks a little different. It's not written in the form y squared equals x cubed plus ax plus b, but you'll have to trust me that this equation could be rewritten in that form. If I did, the coefficients would get even bigger and even uglier. So this is sort of a nice way to leave it. This particular elliptic curve is quite famous for reasons that I'll get into later. But let's run our experiment. One thing you should notice first off, though, and that might suggest to you that there's something special about this elliptic curve, is on the previous slide, we had sort of a roughly uniform-looking distribution. Here, it's very much skewed to one side. Okay? There's a reason for that. So we're going to play the same game. We're going to let our computation run, or replay the results of our computation, and keep increasing the bound on our primes. So we're roughly doubling the number of data points in each interval. And you can see again that even for this very bizarre looking curve that had a very skewed distribution at the beginning, if we let the prime bound get big enough, it again is going to converge to a semicircular distribution. And the sequence of moments again looks like it's converging to the sequence of Catalan numbers with zeros in the odd moments. Okay? You should expect the odd moments to be 0 because the distribution is symmetric. Okay. So this behavior, the phenomenon that we just looked at, was observed back in the early 60s independently by Mikio Sato and John Tate, who conjectured that except for sort of a finite set of very well understood families of special elliptic curves, generically, this is what we should expect to see. We should always expect to see, if we run that same experiment again with a random elliptic curve of our choosing, we should expect to see it converge to a semicircular distribution. This question was open for many years, but it was finally laid to rest by Richard Taylor and his collaborators in around 2008, when they were able to prove that the conjecture made by Sato and Tate is actually a theorem. That if you take an elliptic curve that doesn't have any extra endomorphisms, these are the ones that lie in special families I mentioned, you will always see this semicircular distribution. And Richard Taylor was awarded the 2014 Breakthrough Prize in Mathematics for this work, which came with a $3 million award attached to it. Okay, so hopefully that motivates you to want to prove theorems, so that there's money on the line. Okay. All right. Now you might be wondering what happens with the ones with extra endomorphisms. What do their distributions look like? I don't want to keep you in suspense, so let's go ahead and look at one of these. These curves are also sometimes known as CM curves. This CM stands for complex multiplication. That's a way of describing these extra endomorphisms. And you can see here that the distribution is very different. It's nothing like a semicircle. It's sort of U-shaped, except there's a spike in the middle. And that spike, while it looks very thin, actually half the area of the graph is concentrated in that spike. That it goes up very high, up out the roof of the building. And that's because the trace of Frobenius is 0 at half the primes asymptotically. Okay? And you'll see that the sequence of moments is very different from the sequence of Catalan numbers. It's another sequence 113, 1035, 126, which also has combinatorial significance. I'll leave it to you as an exercise to figure out where that sequence originates. Okay. All right. So I'm not going to get into any of the details, but I just wanted to say a few words about how the Sauter-Tate conjecture was proved. The proof of the Sauter-Tate conjecture builds on techniques that were used to prove a theorem known as the modularity theorem. A special case of this, and for semi-stable elliptic curves, was proved by Richard Taylor and his advisor, Andrew Wiles, in 1995, and then proved in full generality in 2001. And it says that for every elliptic curve, there is a modular form that has the same L function. Now, I'm not going to take the time to define a modular form. You'll get to see some modular forms in a little bit. But we can make this, but a modular form is a complex function, a function of a complex variable that has a lot of extra symmetries. And a priori, there's no obvious reason why it should be connected to elliptic curves. But there's a well-known recipe for, if you're given a modular form, for constructing an elliptic curve out of it. But the open question was, do you get every elliptic curve over Q that way? And this was believed to be true, but it was unknown for a long period of time. And then it was eventually proved in 1995. And again, at this point, you might wonder, well, this all seems very abstract. Why should I be interested in this? Well, this has some nice consequences. I'll just mention the first corollary we get out of this theorem is a solution to a much older problem, one that goes back 400 years. The proof of Fermat's last theorem arises as a corollary of the modularity theorem. Okay. All right, I want to talk a little bit more about this connection. I guess the key thing I want you to take from this slide is that we have a mysterious connection between two different kinds of objects. We have this object that lives in the world of arithmetic geometry, these elliptic curves, and then we have this other object that lives in the world of complex analysis, a modular form, and they're related via their L function. They have the same L function. And I want to make that connection a little bit more precise. So this connection between elliptic curves and modular forms was, in a large part, what gave evidence and made people believe that the modularity theorem should be true, because people tabulated elliptic curves on the one hand and modular forms on the other, and then tried to match them up. And using a recipe that was sort of initially laid out by André Weil and other mathematicians who followed him, they were able to find a very precise match. Every modular form they came up with, they were able to get the corresponding elliptic curve, and every elliptic curve they found, they were able to find a matching modular form. And over many decades, larger and ever larger tables of elliptic curves and modular forms were made matching these two objects up. And computing L functions was how you find the match, computing sequences of traces of Frobenii. These tables of elliptic curves and L functions are now available, and modular forms are now available in what is known as the L functions and modular forms database. I just want to give you a quick glimpse at what some of the things it contains. So here, this is the website you can visit. There are many types of objects stored in the L functions and modular forms database. I'm going to focus, because I want to keep this brief, I'm just going to start off by taking a look at an elliptic curve. So here is a particular elliptic curve. We have a Weierstrass equation. This is just an equation that defines the curve that has a particularly nice form. It has information about its integral points, integral solutions to this equation, and also information about all the rational solutions. It's not immediately obvious here, but this is telling us that the fact that the mod of A group is Z mod 5Z tells us that there are only 5 rational points on this curve. The corresponding modular form has its own homepage and has other invariants recorded associated with the modular form, but the connection between the two is this Q expansion here. So, for example, the modular form, if I write it out as a power series in Q, where Q, you should think of this as e to the 2 pi I z as a complex function defined by this power series, well, the coefficient of q to the 7 was -2. That tells me that the trace of Frobenius at 7 should be -2. And if I go back to my elliptic curve and scroll down, I should be able to see this as well. Yes, although it even gives me the Q expansion of the modular form. That's no surprise, because the way these tables of elliptic curves were initially constructed was by enumerating modular forms and constructing the elliptic curves that match. And it was only after the modularity theorem was proved that we knew that our tables of elliptic curves were actually complete. And you can take this a lot further, so I'll just go for, let's see, here's a list of elliptic curves. We currently have something on the order of 2.5 million elliptic curves in the LMFDB. They're arranged according to a label that encodes what's known as the conductor of the elliptic curve, which is an invariant and numerical invariant of its L function, a sequence of integers that tell us what the equation of the curve is, and then also information about its rational points, which are encoded in this torsion order and also this rank. The set of points on an elliptic curve form a finite abelian group. It has a torsion part, points with finite order, and then a free part, which is an abelian group isomorphic to some number of copies of z, and the rank is the number of copies you need. These rank 0 curves have no rational points other than the torsion points, but if I go down, I will eventually see one with rank 1. Yes, here's one at conductor 37. And if I were to click on that, I could go see the home page for this elliptic curve, and I could see a generator for its set of rational points other than the torsion points. The point 0, 0 can be used to enumerate all of the other rational points on this elliptic curve. Okay. All right. So coming back to, just want to say a few more words about elliptic curves before we move on to higher genus curves. So as I mentioned, the rational points in an elliptic curve are generated by a finite set of points. This is one of the things that makes elliptic curves particularly interesting, is that they have this group structure. The minimal number of generators of infinite order is the rank. And there are a lot of things we don't know about this rank. In particular, we don't even know that there is an effective algorithm that's guaranteed to compute it, although we are generally able to compute it in any particular case. We don't know which values of the rank can occur, and it's a major open question as to whether the rank can be arbitrarily large or whether it's bounded. And number theorists have gone back and forth on this question at least 2 or 3 times over the last 50 years. I'd say the consensus now is probably there's more on the bounded side, but there are still some people who think it's unbounded. We also don't know how often each value of the rank can occur on average, although we know what the answer should be. The answer should be half have rank 0 and half have rank 1, asymptotically, if you order elliptic curves in an appropriate way. Let me tell you a few things we do know about the rank. One is we know that the value of the rank can be as large as 28, and we know that because of the elliptic curve I showed you in the second Sauter-Tate animation. That discovery was due to Noam Elkies. You can see his picture here, or you might be able to find him in the audience. I think he's here. He's also a member of our collaboration. And we know that the average value of the rank, which we think should be exactly 1/2, we can now at least say that it's always that their average value is asymptotically between 0 and 1. This was proved by Manjul Bhargava and Arul Shankar. Bhargava won the Fields Medal, not in the most recent Fields ceremony, but in 2014 for the work that led to the proof of this theorem. Okay. The rank is also the subject of a famous open conjecture, one that has not yet been proved. This is the conjecture of Birch and Swinnerton-Dyer. Birch and Swinnerton-Dyer are computational number theorists like me, and like me, they take great pleasure in actually running experiments on computers. They had a big head start on me, though. They started doing this 50 years ago on the EDSAC-2, one of the very first digital computers. This is the electronic delay signal arithmetic, electronic delay storage arithmetic computer, computational. I think that's something like this, EDSAC stands for. And they've used this computer to do computations to compute ranks of various elliptic curves. And they found that they could relate the rank, at least numerically, to the order of vanishing of the L function at the value s equals 1. And the conjecture they made is that the rank is exactly, which is this algebraic quantity, related to the point structure of rational points on the elliptic curve is exactly equal to the order of vanishing of this complex function. They later made a more precise conjecture that will tell you exactly what the leading coefficient of the Taylor expansion of the function g is, and that formula involves many other invariants associated with the elliptic curve. This question is still open. There's $1 million prize attached to it, so I invite you to forge ahead and see what you can do with this problem. Okay. So the modularity theorem, the connection between elliptic curves and modular forms, is really the first instance of a much broader expansive program known as the Langlands Program that predicts a very profound relationship between objects in different parts of the mathematical universe. So the part that we've really been focusing on is what we would call the motivic world. This is where elliptic curves and algebraic varieties live. Modular forms live in the automorphic world. And there are various ways one can connect the motivic and automorphic worlds. The most direct way is via their L functions. And so the Langlands correspondence predicts a relationship, a precise relationship between objects that live in the automorphic world and objects that live in the motivic world. And this correspondence has only been established in a small number of cases. The modularity theorem is one of those cases. But this is the subject of a lot of ongoing research. Some have referred to the Langlands program as a grand unified theory of mathematics. I think that might be overstating the case, but certainly it's a grand unified theory of arithmetic geometry. I think that would be a fair statement. Okay, so now I want to dig into L functions a little bit more. So the L function can always be defined as an Euler product, where we're taking a product that involves polynomials L sub p for each prime p. And these polynomials can be computed by counting points. So if we take our favorite curve x, or one can even do this with algebraic varieties of higher dimension, we can define what's known as the zeta function of x, which is defined as an infinite series, an exponential generating function, whose coefficients are integers given by counting points on our curve over finite fields. Now, remarkably, this infinite series actually defines a rational function, and the numerator of that rational function, LP, is called the L polynomial of the reduction of our curve x modulo p. And this L polynomial can be computed by counting points. All we need to know is it might look like we need to count points over infinitely many finite fields, but in fact, once we know the point counts up to the genus G, we're done. We can stop. The rest of the zeta function is uniquely determined at that stage. In fact, we don't even need to count points over extension fields of FP. It's enough to just count points mod P if that's all we want to do. Under the Langlands philosophy, this L function satisfies a functional equation and satisfies what is known as the multiplicity 1 principle, which says that its L function is completely determined once you count points modulo sufficiently many primes p. And we can even stick to good primes. There are going to be some primes where this curve doesn't have good reduction. When you reduce mod p, maybe all the coefficients vanish, or maybe it becomes a lower genus curve, or it does something strange. And digging into those special cases is a fascinating subject. It's difficult and complicated. The good news for us is we don't even ever need to do that. Just counting points modulo good primes is enough to tell us what the L function is. You might then ask, well, what does sufficiently many mean? Well, sufficiently many depends on this numeric invariant that I mentioned, the conductor of the L function. And so in the elliptic curve, the first elliptic curve we looked at, the conductor was 11, and that was also the level of the modular form. Okay. So in order to compute L functions, we want to compute these polynomials L sub p, or even equivalently just count points over enough finite fields. This is a well-studied problem. There are many different algorithms to do that. And one can consider the computational complexity of this problem. So there's various approaches one might take. The most naive one would be to just try plugging in solutions, or maybe being slightly careful, plug in one variable and solve for the other variable. This will give you an algorithm that is quasi-linear in P. But it's going to get worse as the genus grows, because you're going to need to count points over more finite fields. You're going to need to go to extension fields. And when p gets big, like if p is getting, say, we want to take p up to 2 to the 40th, that complexity is going to be a little bit depressing, especially because we need to do this for every prime p or for a large number of primes. There are more sophisticated algorithms that take advantage of group structure on the abelian variety associated to the curve, algorithms that use p-adic cohomology, which is maybe worth mentioning. This is another way of reducing a hard problem to one of the two things we know how to do well. P-adic cohomology gives us a vector space, and we can do linear algebra. There is an algorithm that is polynomial time in p, but exponentially increasing in the genus. This algorithm is due for elliptic curves to René Scoffe and was generalized by John Pila. There is no polynomial time algorithm that's known as polynomial in both p and the genus G in general. But remarkably, and this is a 2014 breakthrough by David Harvey, there is an algorithm that will let you, if you want to solve this problem simultaneously for all primes p up to some chosen bound b, the algorithm is actually quasi-linear in the bound b, and it works out to be, on average, polynomial for each prime p. And in fact, the polynomial is the same. It's always log p to the 4th, no matter how big the genus is. The genus is only going to change the constant factors. So this was a major breakthrough. It made it possible to create Sato-Tate distributions and compute L functions for higher genus curves than had ever been possible before. Just to show you maybe one or two quick examples. So this is a genus 2 curve. So the equation now looks like y squared equals x to the 5th minus x plus 1. So we have a degree 5 equation of polynomial in x rather than a cubic, as we did with elliptic curves. And you can see that the distribution here, as we let the primes increase, here we've gone up to 2 to the 32, also seems to be converging to a nice smooth shape. It's not a semicircle anymore. This distribution, actually, there's a random matrix explanation for this distribution. That's also true for elliptic curves. There is a compact Lie group that one can associate to any abelian variety, and a generalization of the Sato-Tate conjecture predicts that the distribution of free Frobenius traces should converge to the distribution you would get if you were to sample matrices from this compact Lie group at random according to Haar measure. And so this sequence of moments is something you can actually compute by understanding the Lie algebra of USP4, the 4x4 unitary symplectic matrices. And this sequence of integers down at the bottom, 1, 1, 3, 14, 84, 594, is actually a two-dimensional analog of the Catalan numbers. And that pattern persists. And so generically, we expect to see a distribution that looks like this. And if I let the genus go to infinity, this is going to eventually converge to a normal distribution. But it's not normal right now, of course, because it's bounded. Here, the x-axis goes from -4 to 4. As in the genus 1 case, we don't always see the generic case. There are certain special families of curves where we see something different. What's interesting is that once you get past genus 1, the number of different things that can happen explodes. There's a lot more different exceptional types of behavior, and these families are no longer just one-dimensional. They become much more complicated. Here, you can almost see in the distribution that there's actually some elliptic curves hidden inside the distribution that we're seeing here. The Jacobian of this genus 2 curve is actually isogenous to a product of elliptic curves, and that's what's creating this unusual pattern. Excuse me, the spike in the middle has density 1/6 in this case. So one can run this same experiment on lots of genus 2 curves. Sorry, let me skip that. And then start to make a catalog of all the different pictures that you see. So this is, if I were an astronomer, I'd be showing you my photo album of all the cool pictures of nebula I've taken when I go out stargazing at night. For me, stargazing involves running my computer and computing these distributions. And then you might ask, are these all the different distributions that one can see? And modulo one unproved conjecture, the analog of the Sauter-Tate conjecture in genus 2 in the generic case, we actually know that if you have a genus 2 curve that is not generic, these are all the special cases. There are exactly 25 that show up over Q, and these are the 25 distributions. There are also other distributions related to not the distribution of the trace Frobenius, but to the quadratic coefficient in the L polynomial, and these give you a larger set of samples. I'm just showing this to let you know that there's more going on there, and the trace Frobenius doesn't tell you everything. It's interesting to look at the entire L polynomial. Okay. And then finally, I promise this is the last histogram I'll inflict on you. This is a Sauter-Tate distribution for a genus 3 curve. This is a histogram that would not have been computationally feasible to produce prior to Harvey's average polynomial time breakthrough. So we counted points on this genus 3 curve for every prime up to 2 to the 30th. This computation took maybe about a week of CPU time. Doing it with any of the previous existing algorithms would have been thousands of CPU years. Okay. David likes to call this the Batman curve because he thinks the distribution looks like Batman. So just to give you a sense, so I'm going to talk about some big computations in a minute and the power of massive parallelism, but the point I want to make with this slide is that computer power is nice, but algorithmic improvements are even nicer. And so what you see here, this slide only goes up to 2 to the 26 because, this is the before, these first two columns are the before, the next two columns are the after. And the generic case is this one, the SPQ stands for smooth plane quartic. And so these are times down here at the bottom, these are estimates of CPU seconds required to count points mod p for every prime p up to 2 to the 26. The histogram I just showed you went to 2 to the 30th. This chart doesn't go that far because I couldn't figure out what these numbers would be because the before algorithms are just too slow to ever get there. These are the after numbers, this 83,000 seconds versus 972 million. So we're already a factor, 1,000 factor here. And if I went down 4 more to 2 to the 30th, we would be more like 100,000 times faster. Okay. This column here is for hyperelliptic genus 3 curves. They're special, they're easier to count points on. So the previous algorithms were faster. And with Harvey's average polynomial time approach, we're faster still. Okay. Okay. All right. Okay, but coming back to the Langlands program, sort of the prelude to proving the modularity theorem and the proof of the Sauter-Tate conjecture that build on the modularity theorem was building up extensive, not just, I mean, on the one hand, it's an evidence. People might characterize it as evidence. Number theorists don't really need to be convinced this is true. We all believe it's true. Collecting the evidence allows you to refine the correspondence in ways that make it more likely that you'll be able to prove it. So for example, it's one thing to say that every elliptic curve is modular. It's a much more precise statement to say exactly what type of modular form you need to use. It should be a weight 2 form with rational coefficients, and the level of the modular form should match the conductor of the elliptic curve on the nose. And when you get to higher dimension, there's a lot more room to play with. So for genus 2 curves, their L functions should correspond to Siegel modular forms, which you need to be very precise about saying exactly what are the constraints you need to put on your in the automorphic world to get a one-to-one correspondence. And there have already, even in genus 2, been several cases where the initial statement of the conjecture was found to be mistaken, and the mistake was found by realizing that there are some special examples of special curves that don't quite fit, and then realizing, we need to modify the conjecture and refine it a bit. So in some sense, to the layperson, the refined conjecture might look more complicated, more confusing, but to the number theorist, the refined conjecture is much better, much easier to prove because you have more to work with. So there's a lot of motivation to want to assemble these tables beyond just convincing ourselves that it's true. It's to understand the connection better. Now, the natural way to do this is to order things by conductor, because the conductor is what allows us to match our tables of curves with tables of modular forms. Unfortunately, we don't know how to do this for any curve of genus greater than, for curves of genus in any genus greater than 1, not even in principle. And there's really two sort of very difficult problems here. The first is that with elliptic curves, there is a standard construction that allows you to turn a modular form into an elliptic curve called the Eichler-Shimura construction. So that if you can list modular forms, you can list elliptic curves, at least ones that are modular, which we now know they all are. Once you get past genus 1, there is no analog of this construction. So even if you knew all of the Siegel modular forms of the appropriate weight and level, there's no obvious way to construct what would be abelian surfaces corresponding to those modular forms. Not to mention, it's also very hard to enumerate these Siegel modular forms. So far, this has really only been done up to conductor about 1,000, which maybe sounds like a big number, but the smallest one is already at 169. There's only like maybe 40 or 50 in that range. And even with those list of Siegel modular forms, or what are known as paramodular forms of a given conductor, matching them to genus 2 curves is very hard. In fact, there are still at least 3 Siegel modular forms that should have matching abelian surfaces, but that we haven't found yet. But we very recently found one, the lowest missing example of conductor 550, as a result of a search for genus 3 curves, which I'm going to talk about in a minute. But so how do we get past this problem? We don't know how. We would like to have a table of curves organized by the conductor of their L function, but we don't know how to do that. So what do we do instead? Well, we search the sky. There are a lot of curves out there. We can just look at all the curves we can see. We could imagine doing a survey of the entire sky, looking at all the curves that might be out there, and try to find the ones that are interesting, the ones that have small conductors. And so to do this, we enumerate vast numbers of curves, generally by just enumerating equations with small coefficients of a particular form. The tricky thing about the conductor is, though, if you just write down a random-looking curve, even with small coefficients, it's likely to have a large conductor. In fact, you have maybe a 1 in a trillion chance of writing down a curve whose conductor is small enough that I'd be interested in trying to compute its L function. That's in genus 3, and it gets worse as the genus grows. Nevertheless, if we are willing to deploy sufficient computational resources, it is possible to find these curves of small conductor and to have some hope of getting a fairly comprehensive list. And so in our genus 2 and genus 3 searches, which we've conducted, we've enumerated a total of about 10 to the 18 curves. That's certainly more than the number of stars in the Milky Way. It's not quite more than the number of stars in the universe, but it's more than the number in our local group, or even in the Virgo supercluster. I think there's maybe like 10 to the 20 stars in the universe, but we're getting close. I will note that that's more, the 10 to the 18, maybe you need a few hundred bytes to describe each curve. There's no way you could store all of that data, even if you wanted to. The entire storage, that's more than an exabyte. That's maybe 100 exabytes. That's more than the storage of the entire internet. Even if you had that much storage, you couldn't afford to write the data to disk, because we're going to spend about 9 nanoseconds on each curve, and there's no way to write data to disk that fast. So the nature of this search is the computer is scanning the sky, looking at gazillions of objects, but we need to structure that scan in a way that it can pluck out the interesting examples and identify them very quickly and just save the interesting cases. And so in the searches that we ran, we kept roughly 100,000 curves of interest out of these 10 to the 18 curves. So maybe 1 in 10 to the 13 curves met our very selective criteria of being interesting enough to save on our precious disk. Now, to make such a computational feasible requires several ingredients. One is very efficient enumeration algorithms. So in order to identify curves with small conductor, computing the conductor is hard. I mean, we can do it, but you're talking about a computation that might take many hours or weeks, and if the conductor's big, it'll take you a long time before you just realize it's too big to even try to compute. So that's not going to happen. Instead, we're going to compute a much easier invariant called the discriminant of a curve. In the case of an elliptic curve, it's very easy to say what it is. If it's y squared equals x cubed plus ax plus b, the discriminant is minus 4a cubed minus 27b squared. For genus 3 curves, the discriminant gets a lot more complicated. For a genus 3 curve, generically, it's a smooth plane quartic. That means it has 15 coefficients. The discriminant is a polynomial in those 15 coefficients of degree 27 with roughly 51 million terms. Now, that might sound hopeless, but yeah, you can actually compute it. If I give you there's a matrix you could write down that would allow you to compute it without actually evaluating that polynomial. It's a 15 by 15 matrix, and you could compute it in a few hundred milliseconds, maybe even a few hundred microseconds if you were really clever. You can't do it in 9 nanoseconds, though. So to do this enumeration efficiently, we want to enumerate not just curves, but curves and their discriminants together in parallel. And we're going to do that without evaluating the discriminant polynomial, but we are, in some sense we are. We're going to build a huge tree, or what computer scientists call a trie. This is the data structure that's used to do autocomplete on your phone. And the way autocomplete works is you type in the first few letters, and then it has a tree that's telling you what are the next possible letters you might type, and it gives you those options. We do the same thing with this 50 million term discriminant polynomial in 15 variables at degree 27. We build a big tree. 51 million's big, but it's not so big. It'll fit in memory just fine. And it's expensive to write down that entire tree and enumerate it. But as you're flipping through curves, you're only changing one variable at the very bottom. And so you're just ticking over one counter. And if you're clever about how you organize this tree, you can compute the discriminant of that next curve on your list with roughly 8 arithmetic operations. And if you encode those arithmetic operations carefully and use the right instructions on Intel processors, you can get this down to a very efficient computation. You can take advantage of pipelining and L1 cache, and there's lots of other optimizations that really do go down to the metal that one does to make this efficient. And then the last ingredient is massive parallelism. So if we're going to search the sky, we want to not use just one telescope. We want to use as many telescopes as we can find, all the ones that Google will give to us, or sell to us, I should say. So I'm just going to describe the most recent computation I ran on, this is on Google's cloud platform. Google will sell you what are known as preemptable instances. So they have a lot of spare capacity most of the time on any given day in any given region. They have servers that are sitting there idle, waiting for people to suddenly decide they all want to search some new term that's become a new viral meme, but most of the time people aren't doing that, and the servers are sitting there doing nothing. And so Google kindly makes those available to number theorists like myself, who are happy to take advantage of their spare computer time, and they do so at a very attractive rate. There is a catch, which is that they reserve the right to steal the computer back from you at any point if they need it. That's why they're called preemptable. So there's no guarantees that you're going to have this computer available to you for any period of time. It might disappear at any moment. So you need to write your algorithm to be completely fault tolerant and recoverable. You need to be checkpointing data or willing to just give up on, abandon that computation. And that's okay. We can do that. And so we put together the code for this search for enumeration of genus 3 curves together with their discriminants. And while there were many months involved in designing all the algorithms and optimizing and testing the code and pipelining the instructions, at the end of the day, the entire computation was run on a single Sunday. I chose Sunday because I was hoping, and a particular Sunday because I was hoping that was a day that Google's computers would be least utilized. And you can see the chart here below shows you when I started. I didn't actually get up that early. I think these are Pacific time. But yeah, so I started in the morning, I think around 9 or 10. And each of these color codes is CPU utilization in different data centers that Google maintains. I used 24, basically any data center where I was able to get quota to run my computations, spread across 9 geographic zones, and fired off as many CPUs as I could because I wanted to get another motivation here with these preemptable instances is you want to grab the resource while it's available and get your computation done and get out. Save your data, be done. You're not allowed to run more than 24 hours ever. And with the average failure rate, you should expect that your CPU is unlikely on average to last 24 hours. It's likely to get stolen from you sometime in that period. So there's an advantage to running lots of instances in parallel, and this was also sort of an experiment to see how fast we could take this. And I should say Google was very helpful in facilitating this process, and I appreciate the assistance they gave us. And so we started out the computation in the morning and fired up. This is servers on servers. We had to spin up many servers whose job was just to spin up other servers, because if you try to fire off 600,000 computations at once, you run into problems. You also have to spread out the data load so you don't have a thundering herd impact with everybody trying to request job information and save state at the same time. So it takes a while for things to get ramped up, but eventually we hit a peak of about 580,000 processors in use at around, I think it was probably around 11 o'clock my time. And then we, of course, were monitoring this closely as it was on, and then we took a break for lunch. And then in the afternoon, we finished up all the instances that hadn't been completed. In fact, I tried to spin up 1 million. And so the 580,000, that's how much resource. I knew I wasn't going to get 1 million, but I figured with a preemptable strategy, your best bet is ask for more than you need, take whatever you get, and then go back and ask for more to fill in the gaps. And that's what we did. Yeah, so I say we, and there is definitely a we. There were a lot of people involved in the prep work for this computation, but I actually ran this computation by myself on the comfort of my own laptop in my own home. So that you can command a tremendous amount of resources on Google Cloud from a single computer. Yeah, I think I won't say anything more about that. So,
what are the different colors?
Yeah, so the different colors are for different data. I don't think there's any meaning for pink versus green other than that these are different data centers. I can tell you the green is almost certainly US Central. I don't know if you're familiar with it. So when you spin up an instance on GCP, you have to identify a region in which your instance is going to live. This is important for people who are, say, running their web server on Google Cloud, where they might want their web server to be close to their customers or close to where they. But for me, I don't care where it is. So I used computers in every geographic zone I could find. So I think there were maybe 4 zones in North America, 2 in Europe, 3 or 4 in Asia and Australia. And I also tried to spread out the timing of how I was using those zones, hoping to avoid peak usage in any particular place. Okay, I think that's all I have to say.